So today we will see the truss analysis example. Okay, this had come in one of the question paper. So the question is analyze the truss completely. Okay, this is just a two-member truss. Okay, and the lengths are given 500 and 400. Okay, we have been given Young's modulus as which is of steel, which is 2 into 10 raised to 5 Newton per millimeter square, and cross section area they have specified as 200 millimeter square. Okay, now one interesting thing over here is the length they have given for this inclined member, the horizontal distance between these 2 points is given as 400 and the vertical distance is given as 300. Okay, and additionally they have given a force, okay, force of 1000 Newton, which is at an inclined angle of 30 degree with the horizontal axis as shown here. Okay, now there would be a confusion how to solve basically and find out the length of this particular truss member. Okay, but since we have been given these two lengths, okay, the horizontal length as well as the vertical length, okay, we have to use the Pythagoras theorem, and since it is 400 and 300, so the hypotenuse, which is going to be the length of the truss member, will be 500 millimeters, 500 millimeter. Okay, so that is not gonna be that difficult to identify. The only confusing part is they have given the force at an angle. So we, as a student, while you are solving in the exam, you might think that this member is also at 30 degrees. Okay, but it need not to be. The force can be applied at any angle, and the length of the member we are going to find out only from the given dimensions. Okay, so then the next thing that comes up is the domain model. Okay, now in domain model, as we know that, okay, there are only two members. Okay, so the two members are having the two supports at the corners, and the one point which is in the middle, okay, is being applied by the external force. So these points where the truss members are being held, okay, those points we will convert into nodes. So I have this node number 1 over here, node number 2 over here, okay, node number 1 over here, node number 2 over here, and node number 3 over here. Okay, now same I have just written over here. So I have this node number 1, node number 2, node number 3. Okay, now since we know that for truss element, I have 2 degrees of freedom, which are the displacement in x direction and displacement in y direction. And similarly, I have the force in x dimension and force in y dimension. Okay, so that is what I have written over here. For node 1, I have u1 f1. For node 2, I have u2 f2. And for node 3, I have u3 f3. Okay, so keeping that thing in mind, okay, we also need to identify the coordinates, okay, for these points. So the coordinates are going to be 0 0. So let us start with the first point being the origin, okay, for our system. So this point comes out to be 0 0. Then we have been given the length. This particular length is 500. Okay, so this is a horizontal member. So the second coordinates will become 500 comma 0. Okay, second coordinates will become 500 comma 0, and the third coordinates, okay, these addition. So the x coordinate of this point will become 900, and y coordinate of this point is given as 300. But since we have taken this as origin, so this will be at the bottom. Okay, this will be at the bottom. So the y coordinate will become negative. Okay, y coordinate will become negative. So it is 900 comma minus 300. And now I know that there are 2 degrees of freedom. Okay, u1 f1, u2 f2, u3 f3, u4 f4, u5 f5, u6 f6, which are the primary variable and secondary variable at each node. Okay, primary variable and secondary variable at each node. So the solution will first begin by identifying the stiffnesses. Okay, identifying the stiffnesses. So this is where we identify the stiffness. So now if we look at carefully, okay, the length of first member is also 500, and when we use Pythagoras theorem, the length of second member is also 500. Okay, so when that happens, my stiffnesses for both the elements will come as same. So that is AE divided by L. Now A is my cross section area, which is 200 millimeter square. E is the Young's modulus, which is 2 into 10 raised to 5 Newton per millimeter square. Okay, and length for each member, as we just calculated, it is 500 millimeters. Okay, so AE by L eventually comes out to be 8 into 10 raised to 4 Newton per millimeter. Then we have to construct a parameter table. Okay, then we have to construct a parameter table. This is a simplest procedure I am saying, so that given the very restricted time in the exam, okay, how you can solve these problems very quickly. These problems may be asked for 10 marks, 12 marks, or 14 marks. Okay, along with, let's say, a another theory question, or let's say another problem. Okay, so then the next step is the parameter table. So parameter table consists of element. Okay, so for element 1, then the sketch of the element. So the first element is in horizontal position, so it is ij. Okay, and then these coordinates, so xj, xi, yj, yi. So for first element, okay, it is 0 0 and 500 comma 0. So it is xj is 500, xi is 0, okay, yj is 0, and yi is 0. Okay, so then I will find out the length of the element. Okay, if the truss members are at inclined positions and they have given coordinates, okay, then you can use the length formula to identify the length of the element, which goes like under root, okay, x2 minus x1 the whole square plus y2 minus y1 the whole square. Okay, so that length we have already identified, which is 500 millimeters. Then I have this L, okay, which we require in the stiffness matrix, truss elements stiffness matrix. So this L, which is nothing but cos theta, this M is nothing but sin theta. So L is what? From the diagram also we can identify the formula for L is xj minus xi upon Le. Okay, xj minus xi upon Le, which is nothing but the cos theta value. Okay, xj minus xi upon Le. Similarly, M is yj minus yi upon Le. So it is the x coordinate difference divided by length. M is y coordinate difference divided by length. Okay, then I have L comes out to be 1, M comes out to be 0, simply because my y coordinate is 0, and since it's a horizontal member, it is not changing. So M comes out to be 0. Then I am writing the value of stiffness, which is 8 into 10 raised to 4. Okay, 8 into 10 raised to 4. Now the next thing is K0. Okay, now K0 is the uncommon factor from the stiffnesses. Now fortunately for us over here, we have same stiffness values even for both the elements. Okay, but sometimes what may happen, if there are 2 elements or 3 elements, you have 3 different values of stiffnesses. Okay, so you will have some common factor and you will have some uncommon factor. Okay, so this K0 being the uncommon factor, what is the common factor we are considering? Common factor is 10 raised to 4. So just to reduce the big numbers, okay, which comes or appears in the stiffness matrix, okay, what we do is we consider uncommon factor inside the matrix. Okay, we consider uncommon factor inside the matrix and we rewrite this matrix, okay, which is of the order L square, Lm, Lm, M square. Okay, and it repeats. Okay, that's what we have seen in a form K0 L square, K0 Lm, K0 Lm, K0 M square, so that the uncommon factor is getting considered inside, and using these three elements I can directly construct my element stiffness matrix. Okay, so it is K0 L square, which is 8, K0 M square 0, K0 Lm 0, because my M is 0. Okay, same for the second element, it is an inclined member Ij. Okay, x coordinate is the xj value is 900. Okay, xi value is 500. Okay, then yj value is minus 300, yi value is 0. Okay, the length we have already found out, which is 500. Okay, L can be found out from xj minus xi upon Le, which comes out to be 0.8. Y M can be found out as yj minus yi upon Le, which comes out to be minus 0.6. Okay, K is again same, 8 into 10 raised to 4. Okay, uncommon factor K0 remains same again, 8, and what we are doing, we are just multiplying 8 inside the matrix. So it comes out to be K0 L square 5.12, K0 M square 2.88, K0 LM minus 3.84. Now writing the parameter table, okay, helps in great extent, because whatever bulk calculation that has to be done, okay, majority calculation happens in the parameter table. After that, we are just compiling the values which we have found out already in the parameter table and writing it in the stiffness matrices. Okay, so the next step is writing the element stiffness matrix. So stiffness matrix for element 1, okay, that is K1. Now as we discussed, okay, the common factor which is 10 raised to 4, that you have to write outside the matrix without fail, okay, without fail. You can't forget this, otherwise the whole exercise will go wrong. Okay, so 10 raised to 4 outside. Okay, now how I am going to identify the order of the matrix? We already know that the order is 4 by 4. Okay, and the elements are L square, Lm, Lm, M square. Now in this particular case, we have just made a modification. Uncommon factor we have included inside. So it is K0 L square, K0 Lm, K0 Lm, K0 M square. Okay, and this four set of four elements tends to repeat. Okay, tends to repeat. So while they repeat at these positions, these values are negative, and again they repeat the same values in the diagonal position. So I construct the element stiffness matrix for element number 1, okay, from these three values, okay, K0 L square, K0 Lm, K0 Lm, K0 M square, minus K0 L square, minus K0 Lm, minus K0 Lm, minus K0 M square, and the remaining values, okay, they just come the similar way. Okay, similarly, we are going to write the element stiffness matrix, okay, for element number 2. So that comes out to be K2 is equal to, again the common factor will remain outside, which is 10 raised to 4. Okay, then I have K0 L square, which is 5.2. Then K0 Lm is minus 3.84. Again K0 Lm is minus 3.84, and then I have this K0 M square, which is 2.88. Okay, K0 M square, which is 2.88. And now I have these signs. Okay, so I need to be very careful with the signs. So these four values, okay, set of four values will repeat. Okay, at these two locations their repetition is with negative sign, and at this location, which is the bottom location, okay, the repetition is with again positive sign. So it comes out to be minus 5.12, 3.84, 3.84 minus 2.88, minus 5.12, 3.84, 3.84 minus 2.88, and minus 3 plus 5.12 minus 3.84 minus 3.84, 2.88. Okay, the DOF numbers, okay, if I am writing DOF numbers, okay, that will help me in compiling these values into a global stiffness matrix. So here the DOF numbers are 3, 4, 5, 6, 3, 4, 5, 6. Okay, they are coming from here. So 3, 4, 5, 6. So this is 3, 4, 5, 6, 3, 4, 5, 6, and the first one came from here, 1, 2, 3, 4. So that way I have 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that helps us in compiling the global stiffness matrix for truss element. So that's what we are going to do, global stiffness matrix for the truss element. Now we know that the order of the global stiffness matrix is going to be 6 by 6. Now how do we calculate that? Okay, we have two truss members. Okay, we have two truss members. Okay, we have how many number of nodes? We have three number of nodes. Okay, so we have already discussed that during the truss element derivation. Okay, number of nodes multiplied by the DOF at each node will give us the order of global stiffness matrix. So number of nodes are 3, DOF at each node is 2. So 3 multiplied by 2 equal to 6. So 6 is going to be the order of my global stiffness matrix. So I know that 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. They are coming from here. 1, 2, 3, 4, 5, 6. Okay. So the common factor will remain outside, 10 raised to 4. Okay. Then I will first write the first stiffness matrix, okay, of the element as it is, okay, at these locations 1, 2, 3, 4, 1, 2, 3, 4. So that is 8, 0, minus 8, 0, 0, 0, 0, 0, minus 8, 0, 8, 0, okay, minus 8, 0, this 8 and this 0, okay, and 0, 0, 0, 0, okay, 0, 0, 0, 0. Okay, now I have, if you carefully observe, okay, these three locations, okay, 3, 4, third row and fourth row, third column and fourth column. So if you can easily observe, okay, I'll just square them up. Okay, this and from this square matrix, this stiffness matrix. Okay, these are the overlapping elements of the stiffness matrix inside the global stiffness matrix. Because if you find the order, okay, it is 3, 3, 3, 4, 4, 3, 4, 4. Same here, 3, 3, 3, 4, 4, 3, 4, 4. So when I have same matrix elements, okay, same matrix elements, okay, at those same places I am going to do a summation, okay, I am going to do a summation. So it is the 8, okay, of this, that is 3, 3 of k1, okay, 3, 3 of k1 plus 3, 3 of k2 plus 3, 3 of k2, that is 5.12, then 3, 4 of k1 minus 3, 4 of K2. So now why minus is coming? Because the sign of 3, 4 for second stiffness matrix is negative. So it is just a summation. Okay, it is just a summation with sign. So if it is minus, it will become subtraction. So it is 0 minus 3.84. Same, the second is 4, 3 of K1 is 0 and 4, 3 of K2 is minus 3.84. So it is 0 minus 3.84 and same 0 plus 2.88. Okay, so that is how I compile this, and the remaining set I write as it is. So 3, 4, 5, 6. So this is minus 5.12, 3.84, 3.84, minus 2.88, and the remaining elements of the stiffness matrix will remain as it is. Okay, that is how I compile the global stiffness matrix. The next step is going to be writing down the global matrix equation. So global matrix equation is always going to be the stiffness matrix K multiplied by the column vector of displacement matrix is equal to the column vector of force matrix on the right hand side. So now I will just solve, okay, whatever is in the bracket I need to solve it. Okay, I will solve, simplify the matrix and write it over here. Okay, which is 8, 0, minus 8, 0, 0, 0, 0, 0, 0, 0, minus 8, 0, 13.12, minus 3.84, minus 5.12, 3.84, then minus 3.84, 2.88, 3.84, minus 2.88, and remaining elements are as it is. Okay, on the right hand side I have all the primary variables from u1 to u6. So u1, u2, u3, u4, u5, u6, and on the right hand side I have again secondary variables which are forces F1, F2, F3, F4, F5, F6. Okay, now if we carefully see the boundary conditions, okay, if we carefully see the boundary conditions, okay, my node number 1 and my node number 3 are fixed. Okay, node number 1 and node number 3 are fixed. So having said that, there won't be any displacements possible because the support is fixed support. So my u1, u2, which are the displacements in x and y on node 1, and displacements in x and y in node 3, which are u5, u6, all are going to remain 0. So u1, u2, u5, u6 equal to 0. Now how I am going to identify the force? The applied force is given at 30 degrees, okay, at node 2. So since it is given at 30 degrees, the magnitude of that force is 1000 Newton applied at 30 degrees with horizontal axis at node 2. So I just have to resolve this force. So the resolution is again simple, 1000 cos 30, 1000 sin 30. Okay, 1000 cos 30, 1000 sin 30. So this 1000 cos 30 is nothing but F3. Okay, 1000 cos 30 is nothing but F3. The value comes out to be 866.02 Newton. Okay, and 1000 sin 30, which is the vertically downward force or resolved force. Okay, it is F4, and since F4 direction we have shown it in the upper direction. Okay, so we will take downward direction as negative. So it is minus 500 newtons. Okay, then what will happen is, okay, I will just include these boundary conditions over here. Okay, and by applying the Gauss elimination method, okay, I can just reduce the order of this matrix. So first row, first column, second row, second column, fifth row, fifth column, sixth row, sixth column. I can just cut, and eventually the matrix order that remains, okay, is only a 2 by 2 matrix, is only a 2 by 2 matrix. Okay, we'll see how we can solve it. So when we apply the Gauss elimination method, okay, we are left with these four elements, okay, in the matrix. That's what I have written over here. Okay, 10 raised to 4, then 13.12, minus 3.84, minus 3.84, and 2.88 multiplied by the remaining values of displacement u3, u4 equal to F3, F4 forces, which we have already found out. Okay, this equation is very easy to solve using calculator. So when we find the answers, U3, U4 values comes out to be U3 is 2.4919 into 10 raised to minus 3 millimeter, U4 is minus 0.014 millimeter. Okay. Now using this, we have to find the values of the forces, okay, which are at the supports, which are nothing but the reaction forces. Okay, so F1 will eventually become, now just need to concentrate on this first row of the global stiffness matrix and this first column. Now we already know that U2, U3, that is U1, U2 and U5, U6 are already 0. Okay, so we know that first and second column and fifth and sixth column are not going to be involved because the multiplying values are 0. Only third and fourth column values will be involved. Okay, so I need to only concentrate on minus 8 multiplied by U3. Okay, eventually multiplied by this 10 raised to 4 common factor will give me F1. So that's what I have written here. 10 raised to 4 into minus of 8 U3. The value comes out to be minus 199.352 Newton. Okay, F2 eventually becomes 0 because all the elements in my second row, okay, are 0. So my F2 becomes 0. Fi similarly will become this 10 raised to 4 outside, okay, multiplied by minus of 5.12 into U3 plus 3.84 into U4. So that's what I have written here. Okay, equal to minus 128.122 Newton. And F6 also similarly will become 3.84 multiplied by U3 minus 2.88 multiplied by U4. The whole multiplied by 10 raised to 4 will give me value of F6, which comes out to be 403.209 Newtons. Okay. Now after calculating the reaction forces, okay, along with the displacements, if you remember, the question has asked to analyze this problem completely or analyze the truss completely. So that calls for finding the values of strains as well as stress. Okay. Now if we have to find the value of strain in an element, okay, we have a direct formula for it. So the formula goes like this. Okay, strain in element 1 is minus 1 into 1. Okay, it's a 1 row 2 column. Okay, minus 1 1 divided by the length of the element multiplied by the transformation matrix, which we have already found out for element 1 as well as element 2. So that transformation matrix multiplied by the DOF matrix, which is nothing but the displacement matrix for the element 1. So it is U1, U2, U3, U4. Okay, now you can multiply them in any order. All these are matrices. So it is 1 row 2 columns. So the order is 1 by 2. This is 2 row 4 columns. The order is 2 by 4. And this is 1 row 4 column. 4 columns 1 row. Okay, 4 columns 1 row. Okay, 4 columns. Sorry, 4 rows 1 column. Okay, 4 by 1 is the order. So 1 by 2 and 2 by 4 I can easily multiply because my columns are matching with rows. The answer that I will get will be of the order 1 by 4. Okay, so that's what I have done here. Okay, this when multiplied by this I will get minus L minus M LM. Okay, minus L minus M LM. Okay, that eventually I need to multiply with the column matrix. Okay, now if you remember, L value was 8. Okay, L value was 8 and M value was 0. Okay, M value was 0. So after doing the calculation, the strain that we get, okay, strain that we get for element 1, that comes out to be 0.0398 into 10 raised to minus 3. Okay, now no unit for strain. Okay, no unit for strain. Similarly for element 2, same calculation I am doing, minus 1 1 divided by LE, the transformation matrix and the DOF matrix for the displacement. This is the value that I get. Okay, strain in element 2 is minus 0.0207 into 10 raised to minus 3. Okay, and then we can directly find the stress values, as stress in element 1 is equal to Young's modulus multiplied by strain, which eventually gives me 7.96 megapascal or Newton per millimeter square, and stress in element 2 is Young's modulus and multiplied by strain in element 2, so that gives me minus 4.157 Newton per millimeter square or megapascal. And as far as the truss element example is concerned, okay, it is expected for you to solve till this end, okay, so that then the answer is completely found out. Okay, and if you are solving till this end, then you can expect, say, good amount of marks if your answers are correct. Okay, so as far as the exam question is concerned, I have just tried and attempted to solve this question
for you so that you can actually understand how the derivation helps us to solve the problems. Okay.